Okay, so in this video we'll talk about a geometric interpretation of quantum bits. So let's remember what a quantum bit is. It's the state of, something like an electron in a hydrogen atom. If it's confined to be then its ground or excited state, which we think of as 0 and 1. The general state of this electron is a superposition of the ground and excited state, which we wrote as alpha 0 plus beta 1, where alpha and beta are complex numbers and they're normalized. So we have the condition that alpha magnitude squared plus beta magnitude squared equal to 1. So now to specify the state we need two complex numbers. This was just one way of writing down that state. Another way we could write down the state is by stacking the two numbers one on top of the other like this, alpha, beta. And now this is very suggestive because it says the state is a vector in a two-dimensional vector space. Okay, so what do we know about this vector space? So it's two-dimensional. It's a complex vector space because the entries are allowed to be complex. And what do we know about the vector? Well, we know that it's normalized. And what's alpha magnitude squared plus beta magnitude squared? This is just the length of the vector, or the square of the length of the vector. So it's a unit vector. Okay, so now let's try to understand a little more about this vector. So let's figure out, what about the vector? What about the state 0? What does it correspond to? Well, in this case, alpha equal to 1 and beta equal to 0. So this is the same thing as the vector 1, 0. What about the state 1, the excited state? Well, in this case, alpha equal to 0, beta equal to 1. So this is the same thing as 0, 1. So if we were to plot it out, okay, so let's just do this with real, let's assume alpha and beta are real because it'll make it easier to draw. So what do we have? Here's our picture. That's the vector 0, the ground state, because it corresponds to that basis vector. That's the excited state, because that corresponds to that basis vector. And now let's just draw a few other vectors in here. So for example, if you had the state 1 over square root 2, 0, plus 1 over square root 2, 1, where would this sit? Well, okay, so in your usual vector notation, you would write this as 1 over square root 2, 1 over square root 2, okay, and it sits like this. That's this vector. How about the vector 1 over 2, 0, plus square root 3 over 2, 1? Okay, so this makes a 60-degree angle, so it sits. But all of this sits, all these vectors are required to sit on the unit circle. Okay, so what have we learned? We've learned that a qubit is a unit vector in a two-dimensional complex vector space. Another thing we've learned is that this notation that we had been using before is really another way of writing vectors. This is called Ket notation. And it was invented by the great theoretical physicist Dirac. So it's also called Dirac's Ket notation. So again, what's this Ket? This thing, and putting the 0 in these funny brackets makes it a vector. So this is just another way of writing the unit vector in this basis direction. This Ket 1 is another way of writing the unit vector orthogonal to it. Now, there's something very nice about the Ket notation for vectors when you're doing quantum computation, quantum information. Because, you see, you want to acknowledge the fact that a quantum bit is, on the one hand, it's a bit, it's carrying information. So you want to say that when it's a ground state, it's encoding a 0. When it's in the excited state, it's encoding a 1. And so this gives you a way of naming these two states as being 0 and 1. But on the other hand, it also acknowledges the fact that the qubit is a more complex object, so to speak. It's, it's not just a bit 0 or 1, but it's a superposition of 0 and 1. And so it's really a vector. It's a unit vector in a two-dimensional complex vector space. And so this notation has the wonderful property of expressing both these aspects simultaneously. Okay, so now let's now that we have this geometric interpretation, let's go back and try to understand what it means to measure this qubit. Okay, so here's our picture again. That's the state 0. That's the state 1, ground excited. Here's the way to write it in usual vector notation. But this is Ket notation. That's the usual vector notation. And now let's define a couple of other states which we want to measure. So, or let's write out, suppose we have a state like this, and let's call this state psi. So now, suppose that this state makes an angle of theta with the 0 state, with the x-axis. Okay, so this angle is theta, and all our amplitudes are real because I'm drawing everything in a two-dimensional real space. So now what's psi? Well, the intercept on the x-axis is cosine theta, so it's cosine theta 0 plus sine theta 1, or if you were to write it in usual vector notation, cosine theta, sine theta. Okay, I'll write, I've been writing it in usual vector notation now for a while, but hopefully soon you'll make a transition where this notation, the Ket notation, will seem perfectly natural to you. Okay, so now what happens when you perform a measurement? Well, when you measure, you see 0. Okay, so the qubit quickly makes up its mind whether it's in the ground or excited state, and it goes into the ground state with probability. This is alpha, so it's alpha magnitude squared. So with probability cosine squared theta, and it goes into the excited state with probability sine squared theta. So your measurement gives you as answer 0 with probability cosine squared theta and 1 with probability sine squared theta. Now, remember that the measurement disturbs the system. So you not only read off 0 and 1, but the state of the qubit actually becomes ground or excited at that moment. Okay, so what's another way of interpreting measurement? So now we have this geometric interpretation of measurement. So when you measure the state, if it makes an angle of theta, then okay, so let's write sine squared theta as cosine squared pi by 2 minus theta. So now what is it saying? Well, you see the state gets projected onto either the ground state or the excited state. With what probability is it going to be projected onto each one? Well, it gets projected onto the ground state with probability cosine squared theta. So with probability the square of the cosine of the angle it makes with the ground state. What about the chance of getting to the excited state? Well, this angle is pi by 2 minus theta. Okay, so it gets projected to the excited state with probability cosine squared pi by 2 minus theta. Okay, so that's the rule of measurement. So when you're measuring the state, it gets projected onto one of these two states, ground or excited, with what probability? With the probability cosine squared the angle it makes with each one. Okay? So that's what a measurement is. It's a projection onto this standard basis, the basis consisting of the ground state and the excited state. Okay, so now that we have this notion of measurement as a projection onto the ground or excited state, we can also start thinking about what would happen, whether we can generalize this notion of measurement. Okay, so here's our picture again. That's the state 0. That's the state 1. Let's say this is our state psi. This is the state of the actual qubit. It's alpha 0 plus beta 1. And now what we are going to do is, instead of measuring it in the 0, 1 basis, what we can do is we can measure it in any basis of our choice, any orthogonal basis of our choice. So instead, let's pick a new basis which consists of this vector u and the orthogonal vector u perp. And we ask, what happens if we were to measure the state psi in this u perp basis? And the answer is exactly what we said before. So if it makes an angle of theta here, then so if we measure psi in the u perp basis, then you see the new state is u with probability cosine squared theta, u perp with probability sine squared theta. What does all this mean, though? What does it mean to measure this state in the u perp basis? Okay, so what it means is you're measuring to see whether the state is this particular superposition of ground and excited or that superposition of ground and excited. So for example, u might be 1 over square root 2, 0 plus 1 over square root 2, 1. And u perp might be, well, now this is minus 1 over square root 2, 0 plus 1 over square root 2, 1. And so what you're trying to tell here is you're measuring to see not whether the qubit is in the ground or the excited state, but to see whether it's in this state or in that state. And what quantum mechanics says is you're allowed to do this kind of measurement as well.